So in the last class, we discussed about Raman spectra, pure rotational Raman spectra, and also we discussed the along with this pure rotational spectra, we discussed about the effect of spin on this nuclear spin on this pure rotational spectra, how it is going to affect the rotational spectra, Raman's rotational spectra. In today's class, we will be discussing further about the same, but for the case of symmetric top molecule and other kinds of molecules. We already completed the diatomic molecule in the last lecture. Okay. So here we will start with this symmetric top molecule. Your professional Raman spectra, Raman of symmetric top molecule. This is pure rotational Raman spectra of symmetric top molecule. Okay. So as we know, the in the case of Raman spectroscopy, molecule must have change in polarization in order to be Raman active. All other molecules which are not having such kind of a change in polarization or polarization in any direction or in any kind of rotation, among these molecules, then such molecules are said to be Raman inactive. Means that if you are using such molecules in order to study the Raman spectroscopy, then that will not give any kind of peak or any kind of spectra at the output. Okay, so we will not get any information about that molecule by using Raman spectroscopy if the molecule does not have any kind of change in polarization. So it's a must condition that the polarization should change in that particular molecule, then only the molecule will be Raman active. Okay. So now if you are considering the case of a symmetric top molecule, as you know, for symmetric top molecule, for example, some CH3Cl, consider this particular molecule. So this is a symmetric top molecule, HCl. So in all other bonds except that CCl bond, all other bonds are CH and it is C. Okay. So this result in that symmetric top structure, those moment of inertia condition that we discussed in the first class of this module. Maybe before that also we discussed about the. So in this case, this bond is different from these three bonds, and it is going to give you that symmetric top condition. If this is also hydrogen, then this will form a spherical top. Anyway, so in this kind of symmetric top molecule, as we know, if the molecule is rotating about this axis, if the molecule is rotating about this axis, is, is rotating like this, then what will happen? In that case, the molecules will not be having any kind of change in polarization because the change is same. Because here all the bonds are hydrogen, so the polarization is not going to change about this axis. So if you are considering rotation about this axis, there is no change in polarizability. There is no change in polarization also. Because when you are applying the electric field in any direction, let's say you can apply electric field in this direction, you can apply electric field in this direction and check what is happening to polarization in that particular uh, molecule. Okay. So in that case, what will happen? In that case, there is, for example, if let's assume that this is the axis that we are considering now. Okay, so with respect to this axis, this molecule is rotating. This molecule is rotating. So then, what is the polarization which is producing in each of these bonds? That will be uh, sorry, the polarization producing in each of these bonds that will be same. Even if you are rotating that. What it means is that the polarizability ellipsoid, if you look at any time, okay, so that will be the polarization ellipsoid will be looking like the same, okay. So the polarization also will be same even if you rotate that molecule in any axis. Okay, with respect to this particular axis. So with respect to that central axis, we do not have any polarization change. Basically, polarization will be there. Polarization for with the HC bonds will be there, but the polarization change will not be there because when you rotate the molecule, we are having same kind of structure on that base of this molecule CH bonds. That structure is same, so the polarization will be same. So even if you rotate that molecule, polarization will not change. Since the polarization is not going to change, such molecule in that particular direction of rotation will not be Raman active. Okay, so that is the first point. So in the rotation about this axis which is passing through the center of the molecule, that will be uh, that will be resulting in no change in polarization. And since or because of this particular rotation is Raman inactive. Okay? And now if you are considering other cases, for example, this particular molecule which is rotating like this, so it is rotation. So in that case, we have this much of this much of bonding which is going to this side, and this particular chlorine atom which is coming to this side. So this kind of rotation that will make some polarization change because the bond at a different position of the molecule uh, that are different. For example, in this case, you are having CCl in this side, so correspondingly, you will be having some polarization in this side. If you consider that ellipsoid, and if you consider on this side of the molecule, then you will be having some different net polarization. And if you are considering the electric field you are applying in this fashion, so in that case, you will be having some polarization. Okay, but when you are changing its position in such a way that this chlorine is coming to this side and this CH bond is coming to this side, then that will result in some different kind of polarizability ellipsoid, which means that the end over end rotation of the uh, molecule, which will result in a change in polarization or polarizability. So that this kind of rotations are Raman active. So this kind of rotations are Raman active because there is some polarization change. Okay. So if you for example if you consider this particular molecule is having some kind of so this is a three-dimensional picture, so we cannot exactly show how it is looking like with that rotations and all those. But you can imagine that because we are having CH bonds in the side of this molecule, and you have CCl bond in the side of the molecule. And when you apply the electric field, the nucleus and the electron, which will be separating, which will be not, which is not separating, which will be displaced because of the action of electric field, positive charge will be attracted towards negative side, and negative charges are attracted towards the positive side, and that will make the polarization in the bond. So that will happen with this CCl bond, CH bond. So, but CH bonds are the crowded in on the side of this molecule. So there will be a net dipole moment in that particular right. But in the above, if you are considering molecule like this, then in this particular case here we have some different kind of polarization, and the net polarization we have to consider in that particular axis when you apply the electric field in that particular. Then in that case, the polarizability ellipsoid will be looking like one manner. But when you are changing that CH bonds to this portion, and the CCl bond is coming down, then the geometry of that polarizability ellipsoid also is going to change. So it will depends on all kind of electric field that you are applying. Then you have to check for the polarization in different directions. So basically, when you are having that the rotation which is about that axis, central axis, okay, or you can say it is the symmetric axis of this molecule, then you can say that the polarization change is zero in that particular rotation. But when you are having that end over end rotation, then you will be having a change in polarization. Then you will be having this molecule Raman active in that the rotation of this symmetric of molecule. And we already know that there is also one figure of how the polarizability ellipsoid will look like for the case of symmetric of molecule text. You can refer that there is no rotation, but how it is looking. We will discuss some with some example also. So let's consider first the mathematical part of this. So for the case of a symmetric molecule, we already know that for this symmetric top molecule, we already studied in microwave spectroscopy. We have the energy in terms of wave number epsilon j comma k. We have two moment of inertia for this case, which is IA equal to IB and IC not equal to 0. You can take it different way accordingly. So we have two different moment of inertia which is not equal to 0 or non-zero moment of inertia components. And so we have J and K which representing the rotational quantum numbers corresponding to both of those rotations. One is along this about this axis, you can see this axis, and the other one is the end over end rotation, that is J. About this axis we have K, rotational quantum number K. Okay, so that will be equal to B into J into J plus 1. This is from that conventional rotational end over end rotation. And we have one more term with B also. So this will be A minus B times K square. This is A minus B times K square. So this K is the quantum number associated with this molecule rotation about this central axis. Okay, and J is the quantum number associated with this end-to-end rotation. So as you know, for this case, I'm not going to discuss all these terms. this A, you know, this A, what is this? We go back and check to this microwave spectroscopy. There is an expression for symmetric of molecule. So I'm not going to explain all those things. With the B, we have the h square by 8 pi square IC. Instead of I, we have IE in the C. Here I will be having that h square by 8 pi square IA in the C, because this is the moment of inertia. Yeah, IA. This IA can be IA will be equal to IC, or you can take IB equal to IC in this particular case, and which is not equal to IA. Depending on that, we have that prolate and orbital structure and all those things. So we check that in microwave spectroscopy. We already discussed. And here the quantum number J can take values 0, 1, 2, 3, etc. as you know. And the K quantum number can take values plus or minus J. Then we have plus or minus J minus 1. Then plus or minus J minus 2. Plus or minus etc. So I will do it one more. So in basically this is nothing but plus J to minus J. So whatever components which are coming, including 0. Okay, so these are the values associated with the quantum number K. This also we already discussed in the case of rotational spectrum, rotational spectrum for microwave spectrum. So that is the quantum numbers which will be having corresponding to this symmetric of molecule. Okay, and the selection rule for this rotation of this particular or transition for this particular symmetric top molecule. Okay, we are talking about the Raman spectra, so it is associated with the Raman spectra. Okay, so selection rule for Raman spectra, and this is through rotation. So I will write selection rule for rotational Raman spectra. Rotational Raman spectra. So what will be this selection rule? That selection rule will be given by delta K equal to 0 and delta J equal to 0 plus or minus 1 and plus or minus. Initially, we had only this plus or minus 2, but in this case, we also have plus or minus 1. So that is an important factor, and what that will change in your spectra that will be coming. So delta K equal to 0 means, and this is also important. This condition is for except K equal to 0 states for delta J equal to plus or minus 2 only. So this K equal to 0 state will be corresponding to delta J equal to plus or minus 2 case only. Okay. If you are having delta J equal to plus or minus 2 only, then only you have to consider that K equal to 0. Otherwise, you should not consider K equal to 0. Okay, because when you are considering K equal to 0, what that means? K equal to 0 means your J is also 0, because your quantum number varies like this: J equal to 0, 1, 2, 3, etc. And K will be equal to 0 only when J equal to 0. Okay, so in that case, if you are looking for that case, then if you are considering delta J equal to plus or minus 1, that will not be valid. Okay, so in that case, when you are considering J equal to 0 state, then you have to treat that case with the delta J equal to plus or minus 2. Which means that when you are having that ground state J equal to 0, you have to consider the condition or the selection rule as delta J equal to plus or minus 2 only. For all other values, you can consider for the delta J equal to plus or minus 1 also for any any other k. But for k equal to 0, we have to consider for any transition to the k equal to 0 state, we have to consider the selection rule delta j as plus or minus 2. Okay, so that is the condition for this. And this delta k equal to 0 is corresponding to, as we discussed earlier also, this is corresponding to that Rayleigh's cap. Sorry, delta j equal to 0 is corresponding to Rayleigh's cap that we have discussed. So that you will get whatever frequency that you send. And delta k equal to 0 means that there is no change in spectra, or we can say that the change in angular momentum about that axis, okay, that top central axis, will not give rise to Raman spectra. That is the meaning of delta k equal to 0. This means that there is can write it like the change in angular momentum. Angular momentum means because of that rotation. Okay, change in angular momentum. Will not give rise to will not give rise to Raman. So if you make any change with respect to that central axis, okay, then there is no change in your polarization, or it will not give you a rise in Raman spectra. That is the meaning of delta k equals. Okay. So the change in angular momentum will not give rise to Raman spectra, and this angular momentum is coming from that the rotation of the molecule. So you can also say the change in rotation of molecule will not give rise to Raman spectra in this case, which means that k, we know this k is, what is this k? This k is coming from the quantum number which is corresponding to this rotation about this axis, central axis or top axis. Okay. So about the central axis, we have that rotation, and because of that rotation, we are getting some kind of moment of inertia and all those things. Uh, uh, in that particular case, in case of symmetric of molecule, we have additional moment of inertia, and we have additional rotation, as you can see here in the figure. We have the rotation about that central axis or top axis, and also we have that end over end rotation. So we have two different kinds of rotations, and when you have that a body which is rotating, we have corresponding angular momentum also. So in that case, uh, if you are considering the angular momentum change, which means that you have some change in your rotational motion. That is that. So where that rotational change is happening, that rotational change is happening with the rotation about this central axis, about this central axis, and the central axis quantum number is nothing but k. The rotation, that particular rotation is represented by the rotational quantum number k. So delta k equal to 0 means this particular rotation does not give any transition. Okay, there is no energy level difference, basically, you can say, because delta k equal to 0 means that 1-to-1 case you can consider. So there is no basic difference which is happening in that particular transition, because that state is that state. So delta k will be equal to 0, which means that even if you are rotating that molecule about that central axis, there is no change in the angular momentum, or no, there is no change in that rotation. Then that rotation, and that will not give any change in polarization. Okay. So in that particular rotation, there is no change in the polarization or polarizability, or or simply polarizability. And because of that, we can say that this in this particular rotation, Raman is inactive. And if you consider the second selection rules as we discussed, 0 is corresponding to Rayleigh scattering. Okay? And plus or minus 2 we already discussed about this particular series of line in case of the rotational spectral pattern. And this condition is also there. This selection rule is valid except k equal to 0 states for delta j equal to plus 1. So if you are considering k equal to 0 state, that is the ground state of that particular common number. And in that case, we should treat only that delta j equal to plus or minus 2. We cannot take delta j equal to plus 1. So there is an exceptional case for this value of k equal to 0, because at that time j is also 0, and you have to consider delta j equal to plus or minus 2 as your transition. Okay, so now we have two different cases. Okay. So let's in the first case, let's consider delta j equal to plus 1. Delta j equal to plus 1. So in this case also we are not considering the negatives, which means that we are considering only the upper to lower, upper minus lower transition, which is equal to positive. Okay, we are considering that the transition which is upper minus lower, and that has to be positive. That positive case only we are considering, as we discussed in the case of the rotational spectra. So delta j equal to plus 1 if you are considering. So this is corresponding to that R branch. This is corresponding to that R branch, because you have delta j equal to plus 1, so it is R branch. And this will be given by epsilon R, the energy with this transition with the delta j equal to plus 1. The transition is having a change in rotational quantum number j, which is equal to plus 1. So that will give you the equation will be like epsilon. And here we have j dash equal to j plus 1 minus epsilon j double dash, because this is the uh, lower state quantum number, rotational quantum number. So this is equal to j. So the difference is j plus 1 minus j equal to plus 1. Okay. So this will give you, and if you substitute these values in that particular equation that is for that Raman spectroscopy, then we will get this is equal to 2b into j plus 1. And in the second case, if you are considering, then you have delta j, which is equal to plus 2, considering only plus positive values. So this is corresponding to S branch. And what is the energy corresponding to this particular transition? Epsilon S is equal to epsilon j dash j plus. This will be plus 2 instead of plus 1, because there should be a difference of 2. This minus epsilon j double dash, which is equal to j. Now this will be given by, so you have to substitute all these values in the rotational uh, energy equation, okay, where we find out the Raman the energy of those pure rotational Raman spectra. Okay, you substitute in that equation. That is nothing but the energy corresponding to pure rotational spectra. So as we did for pure rotational Raman spectras, similarly you have to substitute the same. So we already did this particular case for the pure rotational Raman spectra case, and we got the final expression as b in the some 4j plus 6. Right? So this much of centimeter. This we already derived in the last class, this particular equation. Similarly, you can derive this one also. You have to just replace that j with j plus 2 with the j plus 1. Then you will get the same set, which is 2b in the j. So these are the two energy levels corresponding to this transition, or energies corresponding to these transitions. So this, what this will give, because we are considering transition energy difference between two states. This means that it is the energy difference between two states, which is nothing but the corresponding frequency. If you are considering energy difference between two states, then which is nothing but the frequency that you are measuring, because E is nothing but h in u. So E, if you take A by h, which is h is a constant, so you will get frequency, nothing but a frequency. So if you are considering the energy level between the two levels, which means that you are actually calculating the radiation which is coming out from that two levels, which can be the transition which is happening. Maybe it is absorbing some radiation, maybe it is emitting some. So you are calculating that particular frequency. So if you are having two different energy levels like this, then let's say this is E1, this is E2, and if you are considering a transition like this, means that this particular state is absorbing some radiation with frequency nu and going to this E2 state. Okay? If you are having a transition like this, then which means that from E2, this particular electron or any particle which is coming to the E1 state with emission of some radiation which is equal to. Okay, so if you are calculating what is the energy level between these two energy state, which is nothing but E2 minus E1, if you calculate what is this, then you will get some E that will be equal to h nu. H is a constant. Basically, you are calculating what is nu, that is the radiation which is coming out from this particular transition. Okay, so that will be given by this particular expressions. That will be in terms of centimeter, because it is not in hertz or kilohertz, it is centimeter inverse. So that is the importance of this equation. And if you further look into the spectra that we will get for these two cases, so first we have this R branch. First we are having this R branch. Okay. So for R branch we have 2b into j plus 1. So for this one we have, for this one we have 2b into j plus 1. Now if you are substituting j equal to some value, j equal to, for example, if j equal to 0, what will happen? If j equal to 0, then you will be having the epsilon r will be equal to 2. And for j equal to 1, we'll be having j equal to 1 means this is 2. Then you'll get epsilon r is equal to 4. J equal to 3, then you will get epsilon r is equal to what is this? This is just substitute 3 here. Sorry, this is so 2 plus 1 is 3, 3 into 6, and so on. So this is the spectral positions that we will get corresponding to the R branch of pure rotational Raman spectra corresponding to the symmetric of. And if you look at that spectra, then we'll get it like this. And if you're considering that as mu bar, all those energy levels that we are calculating in terms of centimeter inverse, you consider this as mu bar. And take etc. Which means that it is generally it is representing the frequency. So when you are considering it like this, then okay, we have one problem here. This particular case, I have done a mistake. What is that mistake? We should not take j equal to 0. So this mistake also you should repeat. We should not take j equal to 0, because j equal to 0 state cannot be taken in delta j equal to plus or minus 1 transition. So this is wrong. So we cannot have this epsilon r equal to 2b in this particular case. I will just erase that. So that particular transition is not valid. So don't repeat that mistake. J equal to 0 is not allowed in the case of delta j equal to plus or minus 1 transition. J equal to 0 is not allowed. So only j equal to 1, 2, 3, etc. will be So in this j equal to 1, 2, 3, we have j equal to 1 first, j equal to 2. Then if you are considering j equal to 3, then we will be having 3 plus 1 equal to 4 into 2, 8p. This will become 8, and so on. Okay, so that you will get from here also. From this diagram, this one is representing. So we have for 1, we have this much of intensity. For 2, we have this much of 4, etc. All those. So what we are talking about is that we are considering a single R branch. Within that R branch, we will be getting this kind of spectral lines. Okay? And as you know, this side is anti-stop line, this side is stop line that we already discussed. And this one is the excited frequency. What is the excited? That's the frequency that you are given. So this is corresponding to delta j equal to 0. Okay? So that. And this is these are for the transition of the transition. So basically it looks like this. But if you can resolve all the spectral components, then it will be that lines. So this is the case with R branch alone. We are not talking about P branch here. We are talking only about R branch. Okay, so because we are considering only that positive cases. So in this R branch itself, you have one excitation frequency that you are applied, and then we have additional frequencies also. Similarly, if you are considering the second case for S branch, for S branch also you can substitute those values. But in here, we have delta j equal to plus 2 condition. So in this case, we have j value, which is varying from 0, 1, 2, 3, etc. Because j equal to 0 is allowed in this particular transition. And when j equal to 0 condition, if you are considering if j equal to 0, then that implies epsilon s, that is S branch energy or frequency in the number, which is equal to, what is this? This will be equal to j equal to 0 means 6. This will become 6. Then epsilon s for j equal to 1, that will be nothing but 10p. Then next one is j equal to 2, then epsilon s, that will be equal to 2 means here it will become 2, so 4 into 2, 8 plus 6 equal to 14, and so on. So this is the spectral position in centimeter inverse corresponding to the S branch with the transition delta j equal to plus 2. So that will give me a spectra which can be looked like this. Okay. So these are the j values. Remember this side is j values. So here also it is j value. Remember that here j will start with 0. Here j will be starting with, and we'll be having this kind of a spectral distribution. And remember that one more thing. This is 4b, and this is 6. So see, when you substitute 2 here, then 3, then it will become 3 into 2. And this is 8b. Okay. So the difference between these two is 4b minus 6b, or 6b minus 4b. So the difference between these two is 2b. And the difference between here also 2b. So difference between the lines in anti-stock and stock lines, stock regions. So in that case, we have 2b as our separation between the lines. But for this case, for ES, if you are considering these three cases, we have 10b minus 6b. So here we have difference of 4. Here also we have difference of 40 minus 10. Okay. So in case of S branch, we have the separation between each line, which is 4b. But in case of P branch, we have separation between each of those lines, which is equal to 2b. So here we have a separation of 2b, is 2b. Okay. But when you consider that S branch with the transition plus 2, here we have a separation which is equal to 4. So each of these lines are separated by distance of 4p. So complete spectra, if you look, this is when you look at it separately, but when you consider it as a whole, because when you study Raman spectra, we cannot get it. This is for delta J equal to +1. This is for delta J equal to +2. That is not possible. But we will be getting the complete spectra corresponding to all the transitions. So the complete spectra with the transition of +1, delta J equal to +1 and delta J equal to +2, which will be looking like this. Okay. So also remember that when you consider 2B separation between each of the lines in the case of R branch, if you are considering the S branch, we have the first line at 4B, but which is in case of R branch, we have the first line. Sorry, in case of R branch, we have first line at 4B, okay? And in case of S branch, we have first line at 6B. Okay, and if you are considering the second line in the R branch, then it is nothing but 6B. Okay? So this 6B will coincide with this 6B. Second line of R branch coincide with the first line of S branch. Okay, that also there. So when you consider that, similarly you can also consider this 10B, where it will happen when your J equal to 4, will be getting epsilon R, which is equal to 10. Right. So in that case, this 10B and this 10B will coincide each other, because both of them are having same position. So from that S transition, S branch, similarly for R branch also, for both of these, they are having same the frequency at the same position, same wave number. Okay, so these two frequencies will coincide each other at that position, and the resultant intensity will be larger that particular position. So when you look at the combined spectra, you can see that it is different from the initial two spectra, because in this spectra there is no difference, because it is the starting and which is at 4B. So there is nothing, because 6B is not at obtained. Only at 6B the two lines are coinciding. So you can see that the intensity at 6B, okay, so I will just represent, this is the 2B position, and this line is at 6B position, and you can see the 6B position, it is assumed to have a value. I will just do that here. It is assumed has a value of up to this. Okay, so maximum it can have an intensity up to this. That is what we have obtained earlier. But because of the coincidence of both these spectral frequencies from the R branch and S branch at 6B, we have a larger intensity than the previous cases. You can see here at 6B we have a different intensity. You can see here it is having this much of intensity. Okay. And similarly here also we will be having, I think that is the first line, right? This one is that one. So this is the 6B line, because the first line of S branch is 6B, right? So that is the first line in the case of S branch. So here we have for R branch we have only intensity up to this position. For S branch we have intensity up to this position, up to this point. So the combined effect of these two intensity will be giving you a larger intensity at this much of intensity, and which is higher than what you are getting at the next J value, which is nothing but the next position, just nothing but the 8B. So in the case of 8B, you will be having same intensity, because there is no overlapping happening. But in the case of next line, that is at 8, this is 8b, this is at 10b. Okay. At 10b, we have the overlapping because we have the spectral frequency at 10b in both cases. You have a 10b here, you have a 10b here. So in that case, these two spectra will be at the same position and the total intensity will be getting increased. So we can see that at 10b, we have a larger intensity as compared to the other spectra. You can see here, this is the 10b line. Okay. So this is actually come here, 10b. So that line also will be having increased intensity because of the coincidence of these two spectra at the same position from R branch and S branch. Okay, so this is the spectra corresponding to the symmetric of molecule and the Raman pure rotational spectra of the pure rotational Raman spectra of the symmetric of molecule. That is what we discussed so far.